Example 2 from this section is here to give us a little bit more experience working with the formula for compound interest. It's also intended to help us see how to work with problems where interest is not compounded annually, but is instead compounded more frequently, like semi-annually, quarterly, monthly, etc. So in all the parts for this problem, we're assuming that $750 is invested. So that's our principal or present value. The rate at which the money is invested, the annual rate, is 5.4%, which as a decimal would be 0.054. And we want to know the value of the investment after 4 years. So that's when t is equal to 4. In part A, we want to consider the situation where interest is compounded annually. So M is determined by how frequently your interest is compounded. M is the number of times interest is compounded every year. If we're compounding interest annually, that means we're only compounding once per year. Once we know M, we can calculate I. I is the it's the periodic rate of interest, which in this case happens to be the annual rate. So to calculate I, you just take your annual rate and divide by M. Well, no surprise, in this case, the periodic rate is actually equal to the annual rate because we are compounding annually. In all of these problems is going to be the number of compounding periods in total. Well, in 4 years, we compound interest 4 times if we are compounding annually, so n is 4. So that's not going to be terribly interesting in this problem, but we'll see some more interesting problems in a moment. So the formula for compound interest, let me just write it up here in the corner so that we can reference it later. The formula is A equals P times 1 plus I to the n. So for this particular example, A, the accumulated or future value, is equal to the principal, or the present value, times 1 plus I raised to the nth power. Now, if I plug that into the calculator, I'm going to get $925.60. Okay? So the value of the account after 4 years, if I'm compounding interest annually, is $925.60. So now let's see what happens if we compound semi-annually. Well, semi-annually means twice per year. So M is going to be 2 in this case. I is not our annual rate, but instead our semi-annual rate. It's the rate that how much interest we would collect over a 6-month period. So to get this, we just take our annual rate and divide by M, so we divide by 2. So our 6-month or semi-annual interest rate is 0.027. Now N is the number of compounding periods total. Generally speaking, that is just T times M. So 4 times 2 is 8, or you can think of it as the number of 6-month periods that would be in 4 years. Well, in 4 years you have 8 6-month periods. So I now plug into the formula and I get $750 times 1.027 raised to the 8th power. And if I calculate this, I'm going to get $928.16. One thing you can notice is that the number is actually a little bit higher here. We've invested the same amount of principal at the same annual rate for the same length of time. The only difference between Part A and Part B is in Part B we're compounding interest more frequently. And so that resulted in us having a little bit more money saved. Not a whole lot, but a little bit. Well, one thing you're going to see in the rest of this example is every time we increase how often we are compounding interest, that's going to result in a small increase in our accumulated value. For now, don't worry too much about why that is. We'll explain it a little more carefully later. But the general theme is that all else being equal, compounding more frequently will result in a slight increase in your accumulated value. Okay. So now, let's move on to Part C. In Part C, we are accumulating interest quarterly. So there are 4 quarters in a year, so M is 4. Our interest rate is the annual rate of 0.054 divided by 4. So this gives me 0.0135. And N is the number of compounding periods. That is 4 times 4, which is 16. In 4 years, you're going to have 16 quarters. So we get A equals 750 times 1.0135 raised to the 16th power. And again, I get an answer that is slightly larger than the previous one. $929.48. Okay? So I'm going to continue on and do the remaining parts of this problem. Although if you feel pretty comfortable at this point, there's not going to be a whole lot new in the remaining 3 parts to this problem. So let's see. What do we have? We are at Part D. In Part D, we are accumulating interest monthly. So that means 12 times a year, so M is 12. The interest rate is, the periodic rate is the annual rate, which, just to remind you, that was, let me write it over here in the corner, R. The annual rate, R, was 0.054, and we're looking at a 4-month period, so a 4-year period. Okay, so the interest rate, I, the periodic rate, would be R divided by 12. So if I calculate that, I'm going to get 0.0045. That is the monthly interest rate. So now for N, I need to know the number of months total. In 4 years, you have 48 months. 4 times 12, 48. Okay. So the accumulated value is my initial principal of 750 times 1.0045 raised to 48, and this gives me $930.38. Okay. Now, let's kind of push this even further to sort of an extreme example. Let's assume that we're accumulating interest daily. Now, this is the only example you're going to see in this class where we actually deal with daily interest, but just to sort of illustrate a point, for the sake of an example, let's look to see what happens. Okay, so we're going to be accumulating interest 365 times a year. So my daily interest rate would be my annual interest rate of 0.054 divided by 365. If I calculate that, I'm going to get this really small number. So now N is the number of days in 4 years. So it's 365 times 4. That is 1,460. So A is 750 times 1.000147945 raised to the 1460, and I can calculate that, and I get $930.81. So notice that is slightly larger than what we had if we were compounding monthly, but not much larger, less than 50 cents, 43 cents larger. We could, in theory, continue on and look to see what would happen if we compounded every second or every millisecond. But one thing you're going to see is there's going to be very little change as we compound more frequently. There's actually sort of an upper limit or an upper ceiling that no matter how frequently we compound, we're never going to get past this amount. And that upper ceiling is given to us by continuous compound interest, which we've seen this before in the previous chapter, chapter 2. Just to recap, the formula for continuous compound interest was A equals P e to the RT. Now, when we work with continuous compound interest, we are not assuming that interest is calculated or compounded every day, every minute, or every second. It is under continuous compound interest, we assume that the size of your account is constantly growing. Now, it's not very common that financial institutions actually use continuous compound interest. It's way more common to use something like monthly or daily or something to that effect. But there are a few nice things about continuous compound interest, and one thing is that it's somewhat easy to calculate. But, okay, so let's see what happens if we want to figure out the value of our account using continuous compound interest. We get 750 times, whoops, we don't need that, times e raised to the r, 0.054. T is always measured in years, so t is 4. So then I can calculate this, 0.054 times 4. So in the exponent, I'm going to get 750 e raised to the 0.216. And then I plug that into the calculator, and I get $930.83. So you can see that even if we calculated compounded interest every second, we wouldn't get more than $930.83. That is an absolute cap to how much we could accumulate in this account, regardless of how frequently we compound interest.